Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Hirotaka Ito with us today. Hi, Hirotaka.
Hi, hello. Thank you for having me.
Well, thank you for agreeing to talk about your really lovely article that we'll get to here in a little bit. Hirotaka, where are you located at?
Yeah, now I'm working from at home, so it's Chiba Prefecture of Japan, which is located next to Tokyo area. Yes.
Very nice. And what is your position there, where you're at?
So I'm now working at RIKEN, and yeah, my position is postdoc position. Yeah, I'm working quite a while in RIKEN now. Yes.
Very cool. Very cool. So let's see, it is October 19th in my time zone where we're doing this, but it's October 20th in Hirotaka's time zone when we're doing this. So we're well past equinox. So is it turning into fall, winter there in Japan? Has it started to snow? Does it snow?
Yeah. No, it's not snowing, but yeah, it was actually pretty warm until very recently, last week. But the dropped, now it's pretty cool now. Yes.
Okay,
Yeah.
and we're gonna wait a minute or so because you're kind of frozen here on Zoom. So there you go.
Really?
Oh yeah, now you
Okay.
can. We're good. We're good.
Okay.
You know, sometimes the internet between here and Japan, you know, so it's all good. Very cool. Hirotaka, what do you like to do for research? Okay. Yeah. Okay. You back?
Yes. Sorry.
It happens.
I don't know. Yeah. Okay.
These things happen. Yeah, okay. So we're doing a-okay now. We were doing great before we started, and then all of a sudden we started, then the internet bees came in. So we'll try and go. So what do you like to do for research here, Hirotaka?
Yeah, so I'm interested in the physics of relativistic outflow in high energy astrophysical phenomena. So in recent years, I'm mainly working on the emission process in the gamma ray burst jets, and and also I'm working on so-called shock breakout phenomena. So yeah, such kind of things I do it theoretically, mainly conducting numerical simulations.
Very cool. Very cool. And that is going to bring us to this very lovely APJ article, a global numerical model of the prompt emission in short gamma ray bursts. And Hirotaka, take us away.
Okay, so first of all, I'd like to thank for giving me this opportunity. So yeah, this paper is about emission process in prompt emission in short gamma ray burst. So as you know, gamma ray burst, the emission mechanism of gamma ray burst is actually not established, but in this paper, we explored the prompt emission process in the short GRBs in the context of so-called phosphoric emission scenario by conducting global numerical simulations. Okay, so this is kind of just a summary, but quickly going in the abstract. So what we actually did is that we modeled the, as you know, the short GRBs are expected to happen after the binary neutron star merger. So we, as for the initial we modeled the configuration after the binary neutron star merger, which is consists of black hole accretion torus system at the center, which is surrounded by the expanding ejecta, which is okay. Can you hear me? Okay.
Yes. Your video freezes every once in a while, but we're okay.
Sorry, let me just a moment. Let me try maybe this is due to Wi-Fi. Okay, let me try this mode. are we still connected?
Yes.
Can you hear me?
Yes.
Ah, okay, sorry. Okay, sorry. So
All good.
what we actually did is that we modeled such configurations, and using this as an initial setup, we conducted relativistic hydrodynamical simulations.
Okay.
So what we did is that we evolved this accretion torus black hole system, and also we injected a relativistic jet from the vicinity of the black hole. Yeah, and solved its evolution until it breaks out the ejector component up to the point which it propagates to large distance, up to the point which it becomes, it can release the prompt emission.
Okay.
So, yeah. Then after, as a post process, we solve the radiation transfer calculation within the relativistic outflow by using Monte Carlo method. And yeah, we evaluated the radiation outcome from, by doing such a simulations. So
Very cool.
And okay, maybe I should finish the abstract. Okay, so the main findings, one of the interesting features we found in the simulation is that there's a very strong interaction between the jet and the torus component, which torus also emits an outflow as a wind, and this interaction provides a very strong imprint on the dynamics as well as on the emissions.
Okay.
So, for example, this provides a very rapid time variability in the jet, and also which in turn imprinted in the light curves of the emissions.
Okay.
And that time scale can be compatible with the observations. And also, another interesting important feature found in the simulation is that is on the viewing angle dependence of the emissions. So in the abstract we write the if the observer is close to the jet axis, they see a high spectral peak energy and high luminosity, but as you go off axis, you start to see off axis component which has lower spectral peak energy and lower luminosity, and this viewing angle dependence result in a correlation between the peak energy and luminosity. So if you I'll show in later with the plot, but this slope matches, the slope itself matches pretty well with the observations, but although there's some offset.
Good.
And
very cool.
And we also looked into the polarization properties, and we also discussed the comparison with the GRB 1708 17A, which is the one associated with the gravitational wave.
That's okay. Very good. Cool.
Yeah.
Cool. Okay. So we talk a little bit about GRBs in the opening here in general. And do you want to say anything about the model or the methods?
Yeah. So just as yes, model and method. Yes. So as I said, as for the initial conditions, we consider the black hole torus system, which is formed after binary neutron star merger. So our simulation is it's not general relativity, but we include effective potential which mimics the general relativity. So the torus is bound by the gravity, and it falls into the black hole by the viscosity effect. So it loses angular momentum and falls into the black hole, and then it also emits wind. And then by hand we input a relativist jet from the black hole, and that is solved by using 2D axisymmetric numerical code developed by one of my author, which is Oliver listed here.
Yes.
Okay, I think that's about all for the hydro simulation setup.
And then we launch a jet into that. Okay. Cool. Very good. I'm with you. Ooh, okay, let's take a look at some of the results. Figure 1. What do we got?
So in the figure 1, the uppermost panels are the initial conditions.
Oh,
so
time here, yes. Okay.
Yes, right. So maybe it's pretty okay. The left panel showing it's like just a dot, but at the center this is a kind of black. Yeah, this is black hole, and this surrounding it is a wind. No, sorry, the torus. Torus.
Yep.
And and the bit
got the density. And on the bottom is the electron fraction, or E.
Yes, right.
Okay. So yeah, okay, we're starting off very neutron rich in the torus, right? 0.2 for the electron fraction. That's pretty neutron rich.
Right.
Where do these initial conditions come from? How are these mapped in? Is there some 1D mapping in?
No, we didn't directly map from another simulation, but this mimics the results of numerical relativity simulations, which solve the binary neutron star merger. So yeah.
Okay. Okay, and then in the middle here we got the
it's kind of bit zoomed out view, and it is showing the ejector component. So this is launched just after the merger, and also some new wind component that is launched before the massive neutron star has collapsed into the black hole. So there's actually 2 components. Hard to see, but the elliptical one is the dynamical ejector, and the circular smaller circle one is the massive neutron star wind component.
Yes. Okay. And then we've also got the radial velocity, and we've got the entropy per baryon. Okay.
Right.
And it's low in the middle, and comes out, gets low in the torus, and then it gets high, and then we come back out into the immediate outsides. Okay. So now time goes on. Right. We are at 200 milliseconds.
Right. So at the leftmost panel, you see these small arrows, which is showing the velocity field. So you can see that the the blackish color is the relativistic jet. Yes. Which is, as you can see, it's going outside radially, but outside of the jet, you see the wind component, which is kind of hitting the jet. Yes. So this interaction is actually pretty important. This provides a very strong correlation to the jet, and also it provides a very rapid time variability due to the variable wind evolution. Okay. Good. And very large pressure and a very low density. Okay. Yes. Good. Okay, and what else we got here? We got the this is the zoom out again. This is clearly see jet rolling out here. Yes, it's breaking out. Yes. What do we got here? And then this is Lorentz factor. Yes. So the terminal Lorentz factor is it's a potential for the outflow to be it's the attainable highest Lorentz factor is the terminal Lorentz factor, and it's order of a few hundred. Yeah. Typically, yes. Very good. Okay, so we're breaking out, and then time goes on. We're 2 seconds here. 2 seconds. Yeah. Maybe we can just skip here. Yeah, it just breaks out the larger ejector component. And then we go through a series of log steps here. We've got 10 seconds. Right. Yes. So density versus Lorentz factor. Okay, very cool. Right. Yeah, it's going outside. So we had to solve up to this like few thousand seconds to evaluate the photospheric prompt emission. So you have to cover a large numerical domain for it. So that's Yes.
to 3E8 here in kilometers. Okay, very good. Cool, and we'll just zoom out and take let people get an appreciation for the total picture from 0 to 1,000 seconds. Very cool. Very good. Okay.
Okay. So yeah, maybe we can. Yeah, this is about all for the hydro simulations. So probably we can go to the radiation transfer part, I think.
Okay.
So
I go figure 3, figure 2.
Oh, sorry. Yeah, sorry. I should have introduced figure. Okay, maybe we can skip figure 2. It's a bit detailed. Figure 3 is kind of sorry. Can you go to the figure 3?
I will.
Yeah.
We just have a little bandwidth delay. That's all.
Okay, sorry. Yeah. So yeah, this is showing kind of the average angular structure of the jet.
Yes.
So which is in the free expansion phase. So it's in the it's like it's a structure where the prompt emission coming out, and basically we see a structure which is commonly found in the previous studies. But so sorry, I didn't mention, but the red color is showing the kind of kinetic energy, and the blue color is showing the Lorentz factor. So you have a very fast component at the core region, which is around one degree or so, and then you start to see this decaying part of the jet
as you move out.
Yes.
So at this point, is the total opening angle of the jet 10 degrees, or is it larger than that? Is it 20 degrees?
Yeah. So actually, it's hard to say. How to say? As you can see, there's a gradual decay in the luminosity, energy, and velocity. So it's hard to define what is jet. But if in many papers, with core part of the jet is defined, which is more or less, which is the part which is show high velocity and high luminosity, and that is, I guess, actually in this paper we found it's pretty narrow. It's like between 1 degree to 2 degrees. So yeah,
is the core. Yes. Okay.
Yes, core part. Yes. So, but in other literature, it's larger. Like well, it depends on the initial setup, but it's like 5 degrees or so. So 5 degrees or larger, and this kind of difference from the previous works is that we are thinking that it's due to the wind jet interaction, which strongly correlated the jet. So
yes.
Yeah.
Okay. All right. Good. I'm with you. Okay. Very good. Then we're going to do some Monte Carlo on light curves and spectra, it looks like. Next.
Yes. Right. So yeah, the light curves and spectra is shown in figure 4.
Okay. Let's see. Let's 1 degree, 2 degrees, 3 degrees. Let's go ahead and let's go like that. There we go.
Right. So okay. So yeah, this is showing the light curves and the spectrum as a for different viewing angles. So 0 degrees on axis, and 1 degree is still in the still on the core part, but the 2 degree you start to see this decaying wing part of the jet.
Okay, by 3 certainly. Okay, so we have a light curve, and we have a new spectrum.
Yes, right.
Okay.
So one characteristics is that you see these spiky light curves for 0 degree and 1 degree, and this is again due to the wind and jet interactions.
Okay.
And the time scale can be short as like 10 milliseconds. That can be kind of compatible with the observed time scales. So
on the variability. Yeah.
Yes.
Okay.
So yeah, this is kind of one of the interesting findings in this paper.
Okay, good. Okay, I'm with you. Very good.
Okay.
It goes down and it shifts to lower frequencies as you move away from.
Yeah, exactly.
Right?
So
You're sliding.
right.
Mhm.
So you see, yeah. So as I said initially, yeah, you see high peak energy in the on axis part, but as you go to the wing part, you start to see the lower peak energy.
Slides to the left from about
Yeah.
the 6th EV to 10 to the 4.
Yeah.
That's pretty good.
10 kV. Yeah. So this sequential dependence produces a correlations between the luminosity and this the peak energy. Yes.
Yep. Good. Very nice.
So
That's
yes.
a 2D. That's a 2D Monte Carlo radio transfer.
Yes, but yeah, it's 2D, but basically, essentially, we are solving 3D radiation transfer. But okay, anyway, it's 2D. Yes. Okay.
Okay. Good. Let's see what we got next. We got some correlations. Ooh, we got some observations here, looks like.
Yes, exactly. Yeah.
So let's go ahead and blow that up a little bit. Okay, what do we have here?
So this square plots with different colors is showing our simulation results. So so the black one is on axis, and as the different colors show the different viewing angles.
So trim this way so
Yeah.
it's on axis, and then as we move away from the axis.
Yes.
Okay, yes. And that's
And
energy, and this is luminosity prompt. Luminosity. Okay.
Right.
Yeah, a little variability there.
And you see this error bar plots, and this is observations. But the gray one is a long GRBs, and the cyan cyan green cyan sorry is a short GRBs, and red is also short GRBs, but this is detailed, but this difference is that the red one is considered as in the literature it's classified as secure short GRB, and the light blue one is considered as maybe misclassified short GRBs, which it's just a long GRB with shorter duration. So
okay, yeah, the data would indicate that. And what are the kind of red pink lines?
It's so the solid pink line has a best fit curve, and this dashed line, best fit curve for the observation of lead short GRBs, and the dashed line is the width of the dispersion.
2 sigma or something like that.
I forgot it's 3 sigma. Oh, sorry, I forgot the 3 sigma.
3 sigma. That's from Madi. Yes. Okay. And so we got that in the that's energy release, and then we got the luminosity prompt over here.
Yes.
Things, the longs and the shorts kind of cluster a little closer together in
yes.
Luminosity.
Right. So what we find is the slope itself shows relatively good match, but the normalization seems to show the offset. So maybe this is so maybe this is reflecting the simulation setup, which may not be accurately mimicking the real situation. So kind of we maybe as a next step we want to try to find out the condition that can really reproduce these correlations.
Okay. I'll follow that up when we get there. Very cool. Nice. It's good to see, even just as it is, that it's hitting it pretty reasonably. Very cool. Okay, thank you. And then we got, oh, polarization. You looked at some of the polarization stuff.
Ah, right. Yes.
Oh, yes.
So,
okay.
So yes, so in the simulation, we also solved the polarization, and yeah, these figures are the results for it. And yeah, it's hard to see, but this is showing the degree of linear polarization as a function of viewing angle.
Yes.
And okay, and the non-polarization corresponds to 0 in the y-axis, and the we have a negative and a positive value, but this is reflecting the polarization. Yeah, exactly. The polarization angle. Yes. So it's 2D. So we only have two direction of polarization is only allowed for this due to the axis symmetry. So it's, yeah, that's why we only have, this so negative is like, positive and negative is just also showing the perpendicular directions.
Yes, I'm with you. Good.
Okay.
And they're both the 3 energy bands here, basically.
Yeah, exactly. Yes.
Medium, high. Let's see.
Yeah.
Yeah, you get quite a change in the polarization as a function of energy. Right?
Yeah. That's exactly.
It's not that curve.
Yes. Yeah, that's one interesting point. So maybe this can be, it's observationally challenging, but such kind of signature can be used as a clue to distinguish the emission mechanism of GRB. So if we can measure the polarization as a energy dependence of polarization from the opposition, this can be kind of test to check whether this scenario is good or not.
Okay. Higher energy is going to be closer to the core jet. Is that fair to say?
Sorry. So this is so x-axis is the viewing angle. So on axis is brighter for high energy, but if you go off axis, the high energy part becomes dimmer.
Right.
But the polarization degree increases.
Right. So I was just trying to get a handle a little bit on why does this one behave this way and why does this one appear lower energies kind of flutter around 0 and eventually go positive, right? So you've got
okay, that's a good point. I have to think, but sorry. So it depends on how it's just depending on how these emissions are produced. So actually the polarization is reflecting how the emission is, of course, how the emission is coming out, but it depends on the location of where the dominant emission is coming out with respect to the viewing angle. Sorry. So for a given viewing angle, you have a finite region where you can observe the emission due to the relativistic beaming. And for example, if this part, if this part is suppose this is you are facing this beaming cone, and if suppose this edge part is bright, the polarization angle becomes which way? Sorry. One direction, but if this part is brighter, the emission becomes
more polarized in that direction.
yeah, and why this happens is that yeah, it's low energy part is basically reflecting the how to say
The depth
more
in.
or less, yeah, more or less the thermal emission, but the high energy part you start to see componentized component, and that different mechanism is producing the how to say different preferential direction, yeah,
Right.
for the emissions.
Okay, so it's kind of like an optical depth effect, right? A little bit depends where you're looking.
Yeah.
And what the polarization mechanism is. So the polarization mechanism is changing with energy.
Yeah. Okay. Sorry. Polarization mechanism itself is essentially same, but how to say the preferential direction of the emission is different. So this is changing the properties of the polarization.
Okay.
So sorry, cool. I should have a more clear explanation, but sorry. Yeah,
it's good. Very cool. And then we end off here with comparing to everyone's favorite 170817.
Right. So the one conclusion for this is that we as shown in the plot for the correlations, we more or less align close to the normal short GRBs, but this particular event, the 1708-17A, is a clear far outlier. So its luminosity is like say 10 to the 47 Ls, and while the peak energy is like 200 kV or so. So it's clear, doesn't lie on the correlation curve.
Right.
So that means that that means that our simulation result does not match with this particular event.
Okay.
So what we what we conclude from this result is that we think that the photospheric emission scenario is not compatible with this event, so probably alternative emission process that is not captured in the current simulations. For example, you can think of any kind of process, but for example, you can for example, the shock breakout scenario, which is not captured in our simulation, can be one candidate. That kind of discussion is given here.
Okay. Cool. Yep. There's your photosphere. All righty. Very nicely. All right. Yep. And we covered that. Very cool. All right. Hirotaka, thank you very much for walking us through your very lovely article.
Thank you very much.
And you touched on it a little bit. So let me go there and let me ask you, where does the future hold? And you don't have to spill your next research project, but you could if you wanted to.
Yeah.
Where do we kind of go in the future? For example, how about 3D calculations? Do you think that might change what the 2D result is giving? Do you think magnetic fields might be an important ingredient to add in the future?
Oh, okay.
I mean, just sort of what are the next steps to do in this modeling chain?
Right. So I think you you just kind of said all the things we we have in mind, but yeah, yeah. As you said, our simulation is 2D and 3D. Yeah, definitely 3D simulation is necessary, and recent simulation actually shows that 2D and 3D simulation has an important difference. So I think we should go in that direction. And
do you think the so you were showing like 10 millisecond luminosity variations? Do you think those will stay in 3D, or do you think they get shorter, or do you think they get longer? Do you have a sense of that?
Yeah, that's a very good question. Well, it's hard to answer. Yeah, we naively expect at some degree it will survive, but if you go to 3D, you will have massive mixing, and I'm not sure whether such
We'll go.
mixing will erase all the most of the feature, or how to say,
Enhance them
yeah, it will survive.
or
It's
survive.
something, yeah,
Cool.
we should, yeah, explore.
Okay.
Yeah, yeah, and also as you said, MHD is also, yeah, MHD effect is also important. So we want to explore such issues.
Mhm.
Mhm. Yeah, but and also first of all, our simulation is only one model, so we want to increase number of models to,
Okay.
yeah.
Yeah,
Investigate.
one set of initial conditions. Yeah.
Yes, yes, exactly. Yes.
So let me go there then.
Mhm.
So how long, what kind of computing resources did it take to do that one model? Was this 1 hour on your laptop, or did this take a million hours on a supercomputer?
So it's okay. So we do hydro simulations and also radiation transfer simulation. Both requires a, parallel computing in supercomputer, and it took, I don't have the exact number, but for one model, it's hydro simulation takes how long? More than, okay. I don't have the exact number, but
Yeah, it just is 1 week, 2 weeks, a month.
it's, yeah, not a month, but a few. I think it's all a few weeks. Yeah,
A few weeks. Okay. Mhm.
yeah. And radiation transfer is also okay. It depends on how many cores you use, but yeah, it's like a week or so. Yeah, calculation. Maybe shorter. Yeah, several days. Yeah, I think.
Okay, so sum total to do it all, maybe a month compute resource.
Right.
Roughly.
Mhm.
Okay. Okay. Yeah. So if you want to try 12 different initial conditions, there's a year.
Right, but okay. Yeah, but okay, maybe we can use several computer resources and
Sure.
do it at once. So maybe we can shorten. Yeah.
Yep. Different resources. You can possibly increase the
Mhm.
core count, things along those lines to bring it down.
Yes.
But
Mhm.
nice. Well, I look forward to seeing some of your future articles with exploring different initial conditions, 3D, MHD. That'll all be really, really nice to see.
Yes, thank you. Yes.
Well, thank you. And that'll
Thank
do
you.
on this one, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Okay, bye.